Perfect. So welcome everybody to the next talk of our seminar. It's a great pleasure to have Lisa Sauermann. So Lisa moved much closer to us in Europe, which is a great news for European combinatorics. And Lisa will give a talk about Erdös-Ginzburg-Ziv problem in large dimensions. Please, Lisa.
Thank you very much for the invitation to speak here, and thank you to all of you for coming. So what I talk about today is joint work with Dmitrii Zakharov, who is at MIT. Okay, so the Erdös-Ginzburg-Ziv problem is a classical problem in discrete geometry, a classical extremal problem in discrete geometry. And so the question is the following. Some of you may have seen this question before, but I think there are people from many geographic locations joining, so I don't want to assume that everyone has seen this problem before. So let me start from the very beginning. So the problem asks the following. So given some positive integers m and n, the question is the following. What's the minimum integer s with a property that among any s points in the n-dimensional integer lattice z to the n, there are m points whose centroid is also a lattice point? So recall that for a collection of m points in z to the n, the centroid is simply the average. The average is vectors, so it's if the points are p1 to pm, it's p1 plus and so on plus pm divided by m. And so usually, I mean, for any integer points p1 to pm, this average doesn't need to have integer coordinates, but we are asking about finding m such points so that these coordinates are not just in r to the n, but actually in z to the n. So in other words, we are looking for m points among the s given points so that this average vector, the centroid, is in z to the n. So in other words, so that all coordinates of the sum are divisible by m. So we are looking among our given set of s points for m points p1 to pm so that the sum p1 plus and so on plus pm has coordinates all divisible by m. Okay, so here's again the question. So the question is, how large do we need to make s so that's always possible among any given s points in z to the n to find such m points whose sum has all coordinates divisible by m. So here's an example just to illustrate this with a picture. And because the slide is two-dimensional in my example, n is 2, and because my pictures can be too large in my example, m is 3. And so here you see an example of 4 points, and among these 4 points, it is possible to select 3 points, namely those 3, whose centroid, which is in this point marked by a cross, is an integer point. So among these 4 points, that's possible. But if you think about this for a little bit, you will see that that's not always possible for 4 points in z squared. So for those 4 points, you can't select 3 whose centroid is a lattice point. And if you think about this a bit more, you'll see that even for 8 points, it's not always possible. So here is an example of 8 points where you can't select 3 whose centroid is a lattice point. And in fact, the answer for n equals 2 and m equals 3 is 9. So s equals 9 is the answer to this problem if n is 2 and m is 3. So this example shows that you need at least 9, and one can also show that 9 are enough. Okay, but we don't necessarily care about this for these specific values. This was just an example with some pictures illustrating the problem. Okay, so here's again the problem. And so maybe a priori it's not even clear that there is such a finite number s so that this is always possible. But let me prove this. This is sort of very easy to show. So, so if you have m points, p1 to pm, then this centroid is a lattice point if and only if the coordinates of the sum are all divisible by m. We already saw that. And so now if you take this number s to be this number, m minus 1 times m to the n plus 1, then by the pigeonhole principle, among any s points in z to the n, you can find m points with the same projection in z mod m to the n. So in other words, you can find m points where if you look at the coordinates modulo m, you get the same thing. And then the sum of these m points will have all coordinates 0 modulo m. And so you will find such m points. So this is a very easy pigeonhole argument showing that such a finite number s does exist. And so it gives us in particular, it gives us an upper bound on this number. So in other words, we just showed that the answer to this question is, so it's a well-defined question. There's always a finite number, which is the answer, and that has a name. So this answer to this question is called the Erdös-Ginzburg-Ziv constant, and is noted by this notation s of z modulo m to the n. And so the notation z modulo m to the n comes just because I mean, if you think about it, you can see that it's sort of, you can either ask the problem z to the n, or you can project everything modulo m. Okay, so maybe that's not terribly important right now, but the point is basically you can translate the whole problem into z mod m to the n, and that's where this notation comes from. Okay, and so this very easy pigeonhole principle argument gives the trivial upper bound that this s of z modulo m to the n is at most m minus 1 times m to the n plus 1. And that bound was first observed by Hubbard around 50 years ago. Okay, so here's again the definition, and now with this notation. So s of z mod m to the n is the minimum integer s, so that among any s points in the integer lattice z to the n, we can find m points whose centroid is again a lattice point. And so these Erdös-Ginzburg-Ziv constants have been studied intensively, but there are only very few known exact values. So basically, apart from a finite list of other examples, basically the exact value is only known if n is 1. So that was established by Erdös-Ginzburg-Ziv in 1961, giving the name to this problem. For n equals 2, so that was established by Raya, or if m is a power of 2, that was established by Hubbard. And so apart from a few other finite another finite list of specific pairs of m, these are the only known values. But as is often the case in extremal combinatorics, rather than aiming to determine this number exactly, we want to understand how this problem, so how the answer to this problem behaves as a function of m and n. So we are not necessarily interested in pinning down exactly what this is, but we want to understand how it grows with m and n. So if you fix the dimension n, then Alon and Dubiner showed also now almost 30 years ago that this function grows linearly with m. So if you fix the dimension n, then this grows linearly with this number m of points that you want to select. But in the opposite regime, it's still very much an open problem what happens. So in the opposite regime, if you fix m and let the dimension n be large, it's not well understood how this s of z m to the n grows. And of course, you can also let both of them grow, but typically it's sort of, if you can't even figure out what happens if m is fixed, then it's sort of even more out of reach to understand what happens if both of them grow. Okay, so we are in this talk going to focus on this setting, or on this parameter range of the problem, so where m is fixed and n is large. And so this problem of bounding s of z m to the n for fixed m and large n can then be essentially reduced to the case where m is a prime. So that's some sort of standard reduction. And so for the rest of this talk, we want to consider fixed prime p at least 3 and large n, because for p equals 2, it's also easy. Okay, so that means we are now interested in the following quantity. So we have a fixed prime p and large n, and we are now asking this question: what's the minimum integer s, so that among any s points in the integer lattice z to the n, there are p points whose centroid is again a lattice point in z to the n. And so again, for p points, the centroid is a lattice point in z to the n if and only if the sum of the p points is out coordinates divisible by p. And so that means we can again consider the projections to z modulo p to the n, so in other words, to fp to the n. So that means we now want to find p elements of fp to the n whose sum is the 0 vector in fp to the n. And so that means this problem the answer to this problem is essentially the same up to a constant factor of p minus 1, right? If p is fixed, then p minus 1 is a constant factor. And so you incur such a factor up to such a factor if you account for repetitions among the projections. And so this way you can sort of make some sort of easy reduction and then reduce this problem to the following problem here. So the new problem is, what is the minimum integer s, so that among any subset of s points in fp to the n, there are p points whose sum is the 0 vector. So let me just informally say again, why are these problems essentially the same? Well, you project to fp to the n, and if you have a subset where there are no p points whose centroid is a lattice point, so there are no p points whose sum has all coordinates divisible by p, in particular, among the projections, no point can repeat p times. Because if you have some image repeated p times, then that gives rise to p points whose sum has all coordinates divisible by p, and so the centroid is the corresponding centroid is a lattice point. And so that means if you delete repetitions, you lose at most a p-1 factor. And so that means you then can assume that you have distinct points in fp to the n. So you have a subset of s points of fp to the n, s distinct points of fp to the n, and the problems are essentially equivalent in this parameter range. Okay, so now that means we are basically, again, by equivalently rephrasing this problem, arriving at a problem which sort of belongs to the realm of additive combinatorics. So the problem is now let p at least 3 be a fixed prime and n is large, and we are wondering what is the maximum possible size of a subset of fp to the n without p distinct vectors summing to 0. So that's the same as the problem on the previous slide up to a difference of 1. Okay, so we have already seen that this s of fp to the n that we were wondering about for fixed p and large n agrees with the answer to this additive combinatorics problem up to a constant factor if p is fixed, and so that means we might as well study this problem. Okay, so for the rest of the talk, you can forget about discrete geometry and lattice points. So we are just going to study this problem now. P at least 3 is a fixed prime, n is large, and we are wondering about the maximum size of a subset of fp to the n without p distinct elements summing to 0. And so if we now look at this problem, we might notice that there's an easy lower bound for this, namely 2 to the n, just obtained by taking all 0, 1 vectors in fp to the n. The best known lower bound is a little bit better than this, but roughly of the same form. So the best known lower bound for general p is 2.1398 to the n, up to some rounding. And that's due to Edel and already pretty old. And in the special case of p equals 3, there is a very new bound, which is just a few months old, which is of the form 2.2202 to the n. And so that was an improvement of an earlier bound of Edel, which was 2.217 to the n, and then of Terrell, 2.218 to the n. So basically, it's in the second and third digit where there were a lot of improvements over the last couple of years. And so this most recent improvement is a few months old and was actually published in Nature because it uses artificial intelligence techniques. Mathematically, it uses the same approach as in previous papers, but it finds the particular substructure needed to establish this particular value by artificial intelligence. And anyway, so that's the best known bound. Okay, so
hey, so can I ask a small question? So should we expect for larger p the answer is smaller or bigger?
So that's a good question. So maybe let's save the question for a little bit later. Okay, so because I'm gonna come back to basically that question, and if I forget to address it, then just ask it again a little later. Okay.
Okay, thank you.
Okay, so but let's stay with p equals 3 for now. So why have there been so many papers trying to improve this for p equals 3? So for p equals 3, this question is the same as asking about the maximum size of a subset of f3 to the n, not containing a 3-term arithmetic progression. Because looking at the equation x plus y plus z equals 0 and characteristic 3 is the same as looking at the equation x minus 2y plus z equals 0. And so for p equals 3, this question up here is the exact same as asking about the maximum size of a 3-term progression-free subset of f3 to the n. And as many of you may know, that's a very famous problem to ask about the maximum size of a 3-term progression-free subset of f3 to the n. And this problem is called the capset problem. And more generally, it's a central problem in additive combinatorics to study the maximum size of progression-free subsets of more generally fp to the n or of the integers from 1 to n. So that's a fundamental problem in additive combinatorics. And just to add some more context, so Semeredi proved that for any, so you could not just look for a 3-term progression, but also for a longer progression. So Semeredi proved a while ago, also almost 50 years ago now, that for any fixed k, at least 3, the maximum size of a subset of 1 to n without a k-term arithmetic progression is of the form n, and that was the main result described in his Erdös-Prize citation. So many of you may know this, but the point I'm trying to make here is that studying progression-free subsets is really a very, very central topic in additive combinatorics, and this result is so important that it led to Dmitrii winning the Erdös-Prize. But there's also a lot of, so this result is sort of very nice and clean, but understanding the quantitative behavior of this little O of n term is very much an open problem, and even for K-3, the behavior of this little O of n problem was, this little O of n term was a wide open problem until a recent breakthrough of Kelly and Metcalf from a year ago, where they sort of didn't nail it down exactly, but at least got the behavior of the upper bound to match roughly the lower bound. Okay, but so this is more like a tangent. And so I just want to point out that this problem of progression-free subsets is very, very central in additive combinatorics and very well studied. And so that explains why there was so much literature of the case P equals 3 on the earlier slide. And so also let me now tell you what's known in terms of upper bounds for the specific problem of f3 to the n. So a trivial upper bound is 3 to the m. Schulam proved an upper bound of the form a constant times 3 to the n divided by n. Bateman and Katz improved this by just improving the exponent of this n in the denominator here to some number a little bit bigger than 1. And that was already considered a huge breakthrough, but an even bigger breakthrough was achieved in 2017 by Ellenberg and Reiswald, who improved exponentially upon this trivial upper bound of 3 to the n for this problem. So Ellenberg and Reiswald proved that if you have a subset A of f3 to the n without a 3-term arithmetic progression, then the set can have size at most 2.756 to the n. And so this proof used a new polynomial method introduced by Kotlev and Pach. And Tao then gave a reformulation of this method, which is now called the slice rank polynomial method. Okay, and so more generally, this method and this result was actually not just for P equals 3, but it was more generally for any fixed prime P at least 3. They proved that A is a subset of Fp to the n without a 3-term arithmetic progression, then the size is exponentially smaller than P to the n. So the size of A is at most gamma P to the n for a constant gamma P strictly less than P, which only depends on P and not on n. It's not known whether this constant gamma P obtained from their proof is tight, but interestingly, it's tight for a certain colored version, so for a certain multicolored generalization. And that tightness is due to Kleinberg-Zorn's Bayer Peabody and Marie. Okay, but coming back to what we were interested in this talk, we were interested in the following problem, which we were interested in because its answer agreed to S of Fp to the n up to constant factors for fixed P. So our problem was that P at least 3 be a fixed prime, and what's the maximum size of a subset of Fp to the n without P distinct elements summing to 0. And so if you take P equals 3, those two things are the same. I mean, those two problems are the same. But for larger P, it's a different thing to forbid 3-term arithmetic progressions or to forbid P distinct elements summing to 0. So, so for P equals 3, these two things are the same. And so the result of Ellenberg and Reiswald gives a very nice bound. It gives for this problem up here a bound of 2.756 to the n. And so then we get an upper bound for this Erdös-Ginzburg-Ziv constant of roughly that form. So precisely 1 plus 2 times 2.756 to the n. But for larger P, you can't just sort of look at 3-term progression-free subsets and get a bound for that problem. And so, of course, now a natural question is, could one also apply the slice rank polynomial method for this problem that we are interested in here for P at least 5? If it leads to such a nice bound for P equals 3, can we also do this for P at least 5? And unfortunately, that's difficult. So unfortunately, the problem is that the slice rank polynomial method cannot handle the distinctness condition in our problem. So again, here was our problem. And so we were asking P at least 5 is a fixed prime. We were asking what's the maximum size of a subset of Fp to the n without P distinct elements summing to 0. So in other words, we are asking about the maximum size of a subset A of Fp to the n with no solution to this equation x1 plus and so on plus xp equals 0, where x1 to xp are distinct. So we only forbid solutions where these vectors are distinct. And so this distinct is exactly the problem here. We could ask the following similar looking problem. So we could ask if P at least 5 is a fixed prime, what's the maximum size of a subset with no solution to this, of a subset of Fp to the n with no solution to the same equation, but forbidding all solutions where x1 to xp are not all equal. So that looks very similar. The only difference is distinct versus not all equal. So if you forbid more solutions, if you forbid all solutions where x1 to xp are not all equal, then the slice rank polynomial method beautifully applies and gives a very nice bound. It gives that the size of any such subset is at most 4 to the n. So that's a very good bound. But the proof breaks down completely if you, rather than not all equal, take distinct, so take the problem that we were interested in. So with this distinctness condition, the proof breaks down because the slice rank polynomial method cannot handle this distinctness condition. So for those of you who are familiar with the method, let me just make a small remark why that is. So the problem is that with this distinctness condition, the relevant tensor is not a diagonal tensor anymore, and so one doesn't have a lower bound for this slice rank. Okay, so then of course several people have tried to adapt the slice rank polynomial method to this problem here. And so the first result along these lines has been obtained by Naslund, who introduced a variant of the slice rank method, which he called the partition rank method. Basically, his main motivation for introducing this was this very problem. And so then he showed that A is a subset of fp to the n without p distinct elements summing to 0. Then the size is again exponentially smaller than p to the n. So the size is at most some cp times gamma p to the n, where cp and gamma p are constants only depending on p, and importantly, gamma p is strictly less than p. So that's exponentially smaller than p to the n. So that's exponentially better than the trivial bound that the size is at most p to the n. But this constant gamma p, which is by the way the same as in the Ellenberg-Kreisweit bound for three-term progression-free subsets of fp to the n, this constant grows linearly with p. So this constant is between 0.84p and 0.92p. So this bound is exponentially better than p to the n, but the space here is still linear in p. So it's roughly 0.9p. And yeah, so this bound was then very slightly improved by Jacob Fox and myself. So we improved the constant factor Cp, which is not really important, but we also simplified the proof by deducing this as a black box from this Ellenberg, deducing this from the result of Ellenberg and Kreisweit for three-term progression-free subsets of fp to the n as a black box. So then we'll get a slightly better Cp and certainly significantly simpler proof, but still the bound is the same. So the gamma p is still linear in p. And so that was then improved by myself a few years ago, where I proved that if A is a subset of fp to the n without p distinct elements summing to 0, then the size of A is at most some constant depending on p times 2 square root p to the n. So here now the base is on the order of square root p. So that's significantly better than linear in p. So and this proof combines the slice rank polynomial method with combinatorial ideas. Okay, so here's again that result from a few years ago, and the same proof of this result also gives a multicolored generalization. So similarly to the Ellenberg-Kreisweit result on three-term progression-free subsets, which generalizes to a multicolored setting and is essentially tight in the multicolored setting, something similar happens here. So this proof generalizes to the multicolored setting, and in this multicolored setting, which is a bit technical, so I won't say what it is exactly, but the point is that in this multicolored setting, the bound is almost tight. So there's a lower bound of square root p to the n. So the square root p behavior in the base is sort of tight for this multicolored setting. And so that's similar to the CAPSET problem, and more generally the problem of determining the largest size of three-term progression-free subset of fp to the n. Okay, so for both of these problems, in order to improve the bounds, one needs a proof strategy which is specific to the single set setting, because the bound is already essentially tight in the multicolored setting. So to prove a bound which is better than what we know is the right answer in the multicolored setting, you need a proof which can see the difference between single set and multicolored. And so the problem is that most arguments relying on the slice rank polynomial method naturally generalize to the multicolored setting, so they can't see that difference between a single set and the multicolored setting. And it feels like that is sort of the main barrier to try to improve the bounds for three-term progression-free, the upper bounds for three-term progression-free subsets in FP to the n. And also it felt like that was the main barrier to prove this bound. And so what I want to talk about today is a new upper bound for this problem for p distinct vectors summing to 0, which breaks this multicolored barrier. So we drastically improved the bounds for this problem for subsets without p distinct vectors summing to 0. So here's our bound. It's a little technical looking, so let me say this slowly. So the bound is that for every, so basically the bound is, in the previous bound it was roughly square root p to the n. And so basically the bound here is rather than square root p, you can write p to the epsilon. So for every fixed epsilon bigger than 0, you have the following bound for all primes p and all n. If A is a subset of fp to the n without p distinct elements summing to 0, then the size of A is at most some constant depending on epsilon and p times some constant depending on epsilon times p to the epsilon to the n. So that means the exponential term that was the base of the exponential term that was 2 square root p in the previous bound is now c epsilon times p to the epsilon for any epsilon you want. So if rather than square root p, you want p to the 0.01, you can have it. You'll just have a worse constant rather than the 2. So that's basically the bound here. And so in particular, by this reduction of this Erdös-Ginzburg-Ziv problem in the range of m fixed and n large, we now get a corollary giving basically the same upper bound for this Erdös-Ginzburg-Ziv problem. So for this s of z m to the n. So for every fixed epsilon bigger than 0, one has that s of the m to the n is at most the epsilon m times c epsilon m to the epsilon to the n. Okay, but so by the reductions that I hinted at earlier, this is really a direct corollary of this above. Okay, so this is our result. So here it's stated again. And so our proof combines a consequence of the slice rank polynomial method with a higher uniformity version of the Balog-Semeridi-Goward theorem, and that higher uniformity version is due to Borenstein and Crude. And so now let me come back to Jihan's question from earlier. So let me comment on what are actually the best known lower bounds in this for this problem. So in the setting of the theorem up here, the best known lower bound for the maximum possible size of A is roughly p times 2.1398 to the n for all p at least 3. And as we saw earlier, there was a better lower bound for p equals 3. And so that means there's still quite a large gap in between this lower bound and this upper bound, because this lower bound is of the form p times a constant to the n, whereas the upper bound is of the form that the exponential base here is still dependent on p. And I think that's a very interesting open problem to figure out what the right behavior is, whether it should be constant to the n, where the constant is independent on p, or whether it should be something depending on p to the n. So there definitely needs to be some prefactor which depends on p, but the important problem, I think, is whether there's an absolute constant c, so that for any subset a of fp to the n without p distinct elements summing to 0, one has an upper bound of the form some constant depending on p as a prefactor times an absolute constant to the n.
So Lisa,
and so just to compare,
can I ask a question on that? So
yes.
What if you make the problems of slightly easier? Like, what if you say you want at most p points, or you want at most p squared points? Do you know that at some point like that you do get this absolute constant to them?
So you do. So okay. So let me first answer a different question. So you do get the absolute constant to the n if rather than distinct you say not all equal. So that was on one of the previous slides, right? There was the slide where the distinct and the not all equal was red, and so that was drawing the distinction, how the distinctness really makes the problem much more difficult here. So if you ask for not all equal, and it feels like maybe intuitively that should be roughly the same problem, then you get the absolute constant for to the n. But now to your actual question. So if you say at most p points, that doesn't make a big difference, because you can make the points all lie on some affine hyperplane. So basically, maybe the easiest way to say this is add a dummy coordinate, which is 1 in every point. So add a 1 at the end of every vector. Then you won't be able to find some number of points adding up to the 0 vector where the number of points is not divisible by p. So basically, you can very trivially exclude all solutions where the number of points that you add is not divisible by p. And so at most p points is basically the exact same problem as exactly p points. But now if you take p squared points, it could potentially be easier. Does that answer your question?
Yes, thank you. But I think there's no some value of more points in p where you know the answer is an absolute constant. Then.
Well, I think if you don't restrict the number at all of points, then that's probably.
Oh yeah, and I mean some polynomial in p, I mean, or some function of p, or I don't know, because p is a constant here.
Yeah, so I don't know the answer off the top of my head, but I would assume that there is no bounded number in terms of p. But yeah, I haven't thought about it. So yeah.
Thanks.
Okay, so yeah, so now let me also get back to Jihan's question earlier. How should we expect the answer to be bigger or smaller with p? Well, that's maybe not so clear whether you, like if you, let's put it this way. So it's not so clear, right? Because that's basically the question here. Does it go with p or does it stay roughly the same? Yeah, does that answer your question, Jihan?
Kind of, yes, thanks. But for example, the other question is in a simpler case where you only need, not all of them are equal. You get an upper bound of 4 to the n, right?
Yes.
Is the growth something like still increasing, or it's decreasing, like the exponent when p grows?
Yeah, so in fact,
at the base now.
So in fact, you get something slightly better than 4 to the n. 4 is just a nicer expression. So in fact, you get some minimization problem of a terrible looking term, which is now very hard to say in words, but which you can write down. And now I don't know by heart what the monotonicity behavior of this term is, but you certainly get a slightly different. So for every p, you get some constant to the n, where the constant is a little bit less than 4. But now I don't know off the top of my head which way around the monotonicity of that term is.
Okay. Yeah. Thank you. Yeah.
Okay. Yeah. So one more thing I wanted to say, that in the opposite parameter range, so when n is fixed and p is sufficiently large, then we also know such a bound. So in that range, if p is sufficiently large with respect to n, Zakharov proved that an upper bound of the form 4 to the n times p. So that's also a bound of this form. So one may or may not take the fact that such a bound holds in the opposite parameter range as evidence that it holds here. That's maybe a matter of taste or belief. Okay. Any other questions? Okay, great. So if there are no burning other questions for the rest of this talk, which is, I guess, another 20 minutes or 22 minutes, I want to say a little bit about the proof, because I guess it's hopefully I'm now motivated by the results not completely obvious, and what are some of the hurdles that the proof needs to overcome, like in particular this multicolored barrier. But yeah, so let me try to give you a rough overview about the strategy and how we overcome this barrier. Of course, in 22 minutes, I can't give the proof in all details. And so I just want to give you a glimpse of how it works. Okay, so here's again the theorem. So epsilon is fixed, and A is a subset of fp to the n without p distinct elements summing to 0. Then we want to prove that an upper bound for the size of A of this form. And so, as I already mentioned, one of the proof ingredients is a higher uniformity version of the Balog-Semeridi-Gauss theorem. And so here is an informal version of not the higher informal version of the statement, not the higher uniformity version, but the standard version of the Balog-Semeridi-Gauss theorem, which was proved by Gauss in 1998. And so again, it's just an informal statement. So informally, the theorem says that if A is a subset of fp to the n, which contains many solutions to the equation that x1 plus x2 equals x1 prime plus x2 prime, then there's a relatively large subset A prime of A, so that the sum set A prime plus A prime is not much larger than A prime itself. So that's just informal, because I guess I didn't tell you what many and relatively large means, but it's not important right now, and this is just a proof overview anyway. So let's remember what our task is here. So we need to show that if we have a subset A of fp to the n of size bigger than this, so that's this threshold, this upper bound here, we want to show that if we have a subset of fp to the n which is bigger than this, then it must have p distinct elements summing to 0. That's our goal. So now, unfortunately, this theorem here is rather useless for showing this goal, because if we take a set A of this size, there's no need that this needs to have any non-trivial solutions to this equation here. So for this equation, x1 plus x2 is x1 prime plus x2 prime, there's just, if we take A of this size, no guarantee that we'll have any non-trivial solutions, so let alone many solutions. And so that means this theorem is useless in order to do what we want to do. And so that's the reason we need a higher uniformity version. Okay, so there are multiple different higher uniformity versions of the multi-Balog-Semeridi-Gauss theorem, including one where Benny is one of the authors. But for us, this version, due to Bornstein and Kut, seemed the most suitable for our purposes. So for our purposes, we use this higher uniformity version of the Balog-Semeridi-Gauss theorem due to Bornstein and Kut. So, so here's again an informal version of the statement. So A is a subset of fp to the n, and S is a large subset of k tuples with elements in A. So S is a large subset of A to the k, and we suppose that the sums for these k tuples in S, so for every k tuple x1 to xk in S, we take the sum x1 plus and so on plus xk. We assume that this takes few values, namely at most size of A to the c different values. Then the conclusion of this theorem is that there's a relatively large subset A prime of A, so that the L prime fold sum set, so A prime plus and so on plus A prime, L prime times, is at most well bounded by this, so bounded by some upper bound in terms of the size of A prime for all L prime. So that's the theorem. So now why is that more useful for us? Well, for us that's more useful because if you take any subset A of fp to the n of size significantly larger than p to the nk, then it must have many non-trivial solutions to this equation. So that's just by counting. And so if we have many non-trivial solutions to this equation, then maybe we can imagine that has something to do with with taking only a few values certainly requires this to have many solutions. So that seems roughly related. But maybe the bigger question is now, how do we relate the conclusion of this theorem to what we want to do? So how is having a subset A prime of A, where this A prime fold sum set has size bounded by this, helpful in any way for finding our P distinct elements in A summing to 0, which was our goal? And okay, so the way we make use of this is via an inductive framework, which is basically tailored specifically to the purpose of using this conclusion. So basically, we induct on a condition of the form that L-fold sum sets of A, so sets of the form A plus A plus A and so on L times are small, so that they're bounded by some A to the C. And so that's sort of some condition in our induction, and so then the conclusion of this theorem will make us put us in a position to apply the induction assumption. Okay, and so basically the rough plan will then be that in the induction step via the theorem above, we pass to a smaller to a subset A prime of A, which satisfies this sort of condition, and so then that allows us to apply the induction hypothesis. And so this passing to the subset is by the way, also the key for overcoming this multicolored barrier. Because I told you that this bound with the square root P behavior was tight in the multicolored setting. And so that in the proof, we will need to make some step which is not possible in the multicolored setting. And this is precisely such a step, passing to a subset. So passing to one such subset is not a step that's possible in the multicolored world. And so that is this sort of framework of applying the theorem to pass to a subset, that is the key for overcoming this multicolored barrier. Okay, so as I said, in order to prove what we want, we will use some sort of inductive framework. So we need to induct on some sort of statement where the statement has to do with these L-fold sums being small. And so this statement is very technical looking, so let me say slowly what it means, but feel free to forget it right after I say it. Basically, the idea is we induct on, we have a statement which has in the hypothesis something about L-fold sum being small. So the statement is that for every fixed C, so for every C bigger than 1, there is some L depending on C and some other constant depending on C, so that for every sufficiently large prime P, there is a constant dCp, so that the following holds for all n. And so now here's what's supposed to hold. If A is a subset of Fp to the n, so that the L-fold sum is small, so the L-fold sum A plus and so on plus A is at most A to the C, and A is not too small itself, so A is at least something of the form, basically some constant to the n, so basically has this lower bound, then A must contain P distinct vectors summing to 0. So that's sort of a statement which we are proving by induction, namely by induction on basically C. Now C is a real parameter, so you can induct on it, but if you look at the statement, you see that it's sort of monotone in C, and so you can assume for free that C is H divided by 2 for some integer H at least 3, and so then we can induct on H. Okay, so the statement only gets harder if you make C bigger, and so we can assume C is some integer divided by 2. The reason for divide by 2 is just because we want to start with 3/2 as our induction beginning. Okay, so now let me also hint at why is proving this sort of technical looking weird statement enough for what we actually want. So here's what we actually wanted. So why does this theorem we actually wanted follow from this theorem above? Well, the reason is, so take any subset with size bigger than this. So that size is certainly bigger than P to the epsilon n. Then we can apply the above theorem with C being 1 over epsilon. And then you see that for that particular L that you get in this theorem, this L-fold sum certainly is a subset of Fp to the n, so it has size at most P to the n. And so now by our size assumption on A, that's at most A to the C, right? Remember that C was 1 over epsilon and A was at least P to the epsilon n. So that means we automatically trivially get that this L-fold sum is at most A to the C. And so then that means, and also A has this lower bound assumption here. And so that means that then this theorem tells us that A must contain P distinct vectors summing to 0, which is what we want here. Okay, so in other words, the upshot is that the result we want is a trivial consequence of some technical statement, and where the technical statement has some assumption upper bounding the L-fold size of A. And so then we prove that statement by induction on basically that exponent here in this upper bound. Okay, so here is again the technical statement. And so, so I want to again just give you an overview roughly of what the idea is for how to now prove this technical statement. So we are given a subset A of Fp to the n, and our goal is to show that there's a solution to this equation x1 plus n2 plus xp equals 0, where we take P distinct vectors x1 to xp in A. So how do we get such a solution? The idea is to start with any with some solution to this equation where these x1 to xp are not necessarily distinct. Like if they're already distinct, we're already happy. So let's start with some solution where they're not all distinct, but maybe where some of them or many of them are in some reasonable way distinct, which we'll see later. So we start with some solution where not everything is distinct yet, but then we want to make it distinct. And so how do we do this? So we split the vectors x1 to xp in this solution that we took here into L tuples and fewer than L remaining vectors. So typically P is not divisible by L because P is a prime. But you can certainly with some leftover split this into L tuples. But remember that P is supposed to be very large with respect to C, and therefore you can also assume it's large with respect to L. Okay, and so now we aim to replace each of these L tuples by another L tuples of vectors in A with the same sum. So we are aiming to replace these first L vectors by some other L vectors, these L vectors by some other L vectors, so that for each of the replacements, we preserve the sum. So this sum of those ones is supposed to be the same as for those. For those ones, we replace them by L other ones with the same sum and so on. So that means the equation won't change by making all of these replacements, but our goal is to make these replacements in such a way that afterwards the vectors are all distinct. Okay, And so basically the idea is that using the slice rank polynomial method and some combinatorial arguments, we can ensure that at the start, so when we start with some solution, that we can split it into L tuples so that within each L tuples, the L vectors are distinct, and also that these remaining vectors are distinct. So basically the idea is, and I'm not really telling you why, but basically the idea is using the slice rank polynomial method and some combinatorial arguments, you can't necessarily generate a solution to this where everything is distinct, but you can generate a solution where there are not so many repetitions in the sense that you can split it into L tuples so that within every L tuples things are distinct, and then the fewer than L leftover vectors are also distinct. Okay, and so now in each step we want to replace one of these L tuples by another L tuple of vectors in A with the same sum, so that the vectors in the new L tuple are also distinct. And in addition, they're supposed to be distinct from all the other vectors in the current solution, right? We want to prove. We want to get that our new L tuple that we take here is not having a repetition with anything we already had. Okay, and if we can do this step by step for each L tuple, then at the end we obtain a solution where everything is distinct. So then we would be happy, but of course we might get stuck while trying to do this. So that means we might get to a point where we cannot find a new L tuple with these desired properties. So the desired property are the vectors inside the new L tuple are distinct. They're distinct from all the other current vectors, and they have the correct sum. Okay, so what does it mean to get stuck? So that means that if we get stuck at some step, that means that given the desired sum W, so suppose we want to replace this, we're looking for an L tuple with that same sum W as this one. So given the desired sum W for the L tuple, we are looking at all subsets y1 to yl of A of size L, which have the correct sum W, and we want to find one such subset with that sum where the vectors are distinct from all the other current vectors in the solution. And so suppose we can't do this, then that means all such subsets can be covered by the at most p other currently appearing vectors in the solution. And so that leads us to the following definition. We call a vector W bad if the family of subsets of size L of A with sum W, so this family of subsets W y1 to yl with of size where these y1 to yl are distinct, so this is a size L subset, and y1 plus and so on plus yl equals to W, where this family has a cover by at most p vectors in A. So if W is not bad, then we can automatically, so if W is not bad, then there's no cover of size p, and so we cannot get stuck in this way. Okay, so we can only get stuck if we are currently at a bad sum that we're trying to replace. And so now let's extend this definition. We call an L tuple bad if the sum is bad. So that means when we are...
Can I ask some question? So when you do this procedure, can you at least guarantee that there are many this y1 up to yl which give you this W, right? Because if there are very few of them, then they can easily be pinned by few vectors, right? Can you at least guarantee that there are many of them? This hypergraph can still have small cover, but
yeah. So I'm not sure. I haven't wondered about this, but sort of how many there are is really not maybe the right thing. Like if there's fewer than p of them, then clearly there's a cover of size p.
Of course.
But really, the number of them isn't really the correct. Measure. Like what makes you stuck is really having a small cover.
Okay.
I think just by counting. Okay, so I haven't really thought about this question. There might be an easy answer just by counting. But even if you can guarantee there are many, you're still stuck if there's a small cover. Okay, so yeah, so here's some observations. So if at the start of our process, none of the L tuples in the solution is bad, then by the way we set up this bad thing, then we can always do the replacement, right? Because if it's not bad, then there's not a cover of size p, so we can do the replacement. Every replacement step is successful, and we arrive at what we end. We arrive at the end of the process at what we want, so we arrive at a solution with distinct vectors. So if there were only, so now comes a counting thing. So that wasn't exactly the counting Benny suggested, but it's another kind of counting. So if in total there are only very few bad L tuples, then by a probabilistic sampling argument, we can pass to a fairly large subset A prime of A, so that there's no bad L tuple surviving on the subset. So this badness is still defined in this original way with respect to A, but the point is, if there's only very few bad L tuples to begin with, then by some easy probabilistic sampling, you can find a fairly large subset A prime of A, so that there's no bad L tuple y1 to yl and A to the L, so that y1 to yl are all in A prime. And so in that so that observation already suffices for the induction beginning, but for an induction step, we also need to deal with the case where there are many bad L tuples. And so basically the idea is if there are only few and you find this A prime, then you can start with a solution to this equation in A prime, and then you can do the replacement, because then that solution doesn't have any bad L tuples. Okay, so I have only 4 minutes left, so I can't go through, so I have some slides with a few more proof details. So let me just jump over some of them and just sort of selectively point out a few more things in the last 4 minutes. So this basically, this slide is talking about how using the slice strength polynomial method, you can start in the beginning with a solution. You can sort of basically, if your set is large enough, ensure that you find a solution that in every L tuple, the vectors are indeed distinct. And so maybe that's not so important right now, because for time reasons, I'd like to skip this. And then the bottom of the slide sort of talks about the induction beginning. But since the induction beginning is sort of less interesting than the induction step, let's also skip the induction beginning. Okay, and so let's instead talk about the induction step. So here, because that's sort of the hardest part, and that's sort of where everything comes together. So for the induction step, now let's sort of, there are some constants here. So C was this constant that we induct on. So we write C equals H over 2 and induct on H. So the induction beginning was H equals 3. And so now in the induction step, H is at least 4. And so we assume that we already proved the theorem for H minus 1. Okay, so don't worry too much about the exact details of these terms. I just want to sort of roughly communicate the idea. So now L is sufficiently large with respect to C. And so we consider, so because that's what's happening in our theorem, we consider subset A of Fp to the n, where this L-fold sum is at most A to the C, and A is also large enough, and so has this lower bound. And so the assertion of the theorem now is that A has P distinct vectors summing to 0. So now here's again this setup with these bad things. So just to repeat, so a vector is bad if the family of subsets of size L, subsets of A of size L, with this sum W has a cover by at most P vectors in A, and an L tuple of distinct vectors in A is bad if the sum is bad. And so now here's again what we said before. So if there's only few bad L tuples, then we can do a probabilistic sampling argument to pass to some subset A prime of A, which has still some reasonably large size. And so that within A prime there is no L tuple which is bad in the sense here. And so then within this A prime, using the slice strength polynomial method and the combinatorial arguments, you can find a solution to the desired equation, this x1 plus and so on plus xp equals 0, so that you can split it into L tuples, so that within each L tuple and also the vectors are distinct, and also the remaining vectors are distinct from each other. And so then you can do the replacement because nothing is bad, because in A prime there was nothing bad. So the maybe more interesting case is what happens if there are many bad L tuples. So now here's the trick of what you do then. So if there are many bad L tuples, then each of them you can write in the form y1, and so on, yl minus 1, z, where the sum is bad, and z is one of, so up to permuting, you can write it in that form, and where z is one of the p vectors in the cover for some w, right? So the tuple being bad means that the sum is bad, and that the sum is bad means that all tuples with the sum have a cover by p vectors. So we can write this particular tuple so that z is one of the vectors in this cover. And so now, if there's many such bad tuples, then there's many tuples of this form where the sum is bad and z is one of the p vectors in the cover, but now we can do some counting. So how many choices do we have in total? Well, we have at most L times so L-fold sum A, so which was at most A to the C choices for W, right? Because that was our assumption in the set A that this L-fold sum was small. So there's at most that many choices for W, but fixing W or choosing W, there's at most P choices for Z. And so that means in total, there's at most not so many choices for W and not so many choices for Z. And so that means there must be many L-1 tuples by 1 to by L-1 with the same Z and W. And so that means they must have the same sum. So basically by some counting, the upshot is by some counting, we can find many L-1 tuples by 1 to by L-1 in A to the L-1, so that these sums are concentrated on relatively few different values. And so now that puts us in the position to apply the theorem of Bornstein and Root. So again, I don't want to go through the exact details, but the point is now we found many L-1 tuples with only few different sums. And so then that theorem exactly tells us that we can pass to a subset where this L prime fold sum is small. And so that now puts us into the setting to apply the induction hypothesis, because the parameters were chosen in such a way that this bound that we now get here for the L prime fold sum is C minus a half. So it's strictly, so it's exactly our value, other value C from the induction hypothesis. And so that means by the induction hypothesis within A prime, we can find a solution to this equation with distinct vectors in A prime. And so that automatically then gives a solution to this equation with distinct vectors in A, and we are done. So that's roughly an overview of the proof. And so thank you for your attention.
Thank you, Lisa. So let's, sorry, didn't mean that. Yeah, so thank you, Lisa. So questions, you can unmute yourself and ask question.
Hi, Lisa.
Hi.
So which step do you think is the most crucial part you need to have really a growth of the base number?
Probably multiple steps even. So, we try to think, of course, whether we could improve this proof to get constant to the end, and seems difficult for several reasons. Yes, so it seems like some substantial new ideas are needed. So I think so basically, let me try to point at one of the issues, and it might not even be the only one. So in this, when you try to split into L tuples so that within every L tuple, your solution is distinct, obviously, within each L tuple, the vectors are distinct. Obviously, in order to do this, at most the 1 over L fraction of all vectors in the solution can be the same, right? Because otherwise you can't split them on different L tuples. But so basically, you're trying to find a solution to this, where maybe not everything is distinct, but every vector occurs at most P over L times. And so in order to get that by the size rank polynomial method, so maybe there's a better way to do it, but the only way we knew how to do this requires a lower bound here, which is of this form. So where here you have a constant depending on L. So, okay, so this lambda here you should think of as 1 over L. So you have constant depending on L to the n. So in order to get an absolute constant, that would mean you could take your L to be not growing with P. But if you have L not growing with P, then you So you, in order to get an absolute constant, this L would need to be an absolute constant. But yes, in order to get that, you arrive again at a problem, basically the same problem why you can't apply the Gauss Gauss theorem in its original form, because then you might not have any solutions to. So you might not have any non-trivial solutions to 2 K tuples or 2 L tuples having the same sum.
Yeah, thanks.
So Lisa, actually following on this, so basically you're saying that it's equally hard to find, all distinct, or say, I don't know, P over 3 distinct, right? So that's roughly.
No, I'm not saying that. I'm just trying to say one of the ingredients in our proof of finding P distinct is finding P over 3 distinct. But I think it's not sort of, there's many, going from P over 3 to P, I think is still very hard. Let's put it this way. I think, so basically, I didn't sort of actively think about this question, but the methods, and so basically, this P over 3 distinct result, or I mean, more generally here, this P over L distinct result is proved by roughly the same technique as my earlier paper from 3 years ago. And so I think if you had asked me this question 3 years ago, I would have probably been able to figure out how to prove P over 3 distinct. But it's still very hard to go from P, everything appearing at most P over 3 times to everything appearing at most once. So, so it's not the same difficulty, but this particular thing goes in as an ingredient, and that ingredient already sort of forces you to take P to the epsilon rather than P absolute constant. Does that make sense?
Yes.
Yeah. And the other question is, so you define bad to be, you have a cover of P points. And does this P play any important role in the proof or not? Like, for example, if you replace P by 2P, does everything still work, or just curious?
Yes, I think so. So, I mean, the reason it's P is just because the reason it's P is because your motivation for setting up this definition is that you want to replace.
Yeah.
Okay, I had a picture.
Yeah.
You want to replace this, right? And there's at most P other things you want to avoid. In fact, it's P minus L things you want to avoid. And so P is an easy upper bound on the things you want to avoid. And it's important for the proof that it's sort of something constant, right? And I mean, that's not something growing with n, say. But whether it's P or 2P or P squared, I think should not make a difference.
Okay, thanks.
So it would sort of maybe affect the terms, like, okay, these slides, I guess we skipped all terms, but there are some terms here like P to the 10 and so on. That would probably be affected, but
okay,
yeah.
Thank you.
Great, more questions? So if not, maybe let's thank Lisa again, and we can stop recording.